Okay, very welcome to all of you, and I hope everybody is fine in this cold wave that we have. I think the temperatures were down to -5 degrees Celsius yesterday. So let me take you to a universe in which you can walk anywhere. There is, if you imagine that there is a universe, and in this universe there is one fellow. This one fellow is walking in this universe. There are no constraints, there are no forces. He feels everything is fine. Whatever he wishes to do, he does it. But suddenly a point comes, not a pit, not a hole, not a cosmic hole, a point. And at this point, this fellow feels tremendous potential. Maybe this potential is gravitational potential, or it is electrostatic potential, but he feels this potential on only just one point. And then he moves on. What? I have my own. Yeah. So you have a person walking in a universe where there is no force, nothing at all. Whatever this person wishes, he does. He doesn't feel any force. And a point comes. At this point, he feels. And then he leaves that point. When he leaves that point, he feels as if nothing had happened. This is your Dirac delta potential. So everywhere this person feels nothing, it's zero everywhere. The person, whatever he wants to do, he does it. But at a point, it's a point. It's not a pit. It's not a hole. It's not a cosmic hole. It's just a point. And at this point, it feels. And then when he crosses it, he goes back to the same universe. But there is nothing that is hurting him, exerting him, or creating any kind of disturbance to him. Now, this kind of potential is called as Dirac delta potential. Right? So you must have seen it. If I take a Dirac potential, I may represent it by a single line, because this is a point. And if I choose this as x equal to 0, at this point, you will feel whatever you want to feel. You will feel the potential, right? But away from this or ahead of this point is nothing. The universe is open for you. There's nothing. This is how the Dirac potential behaves, right? So you know the two basic properties of this Dirac delta function. So since I said I chose an imaginal potential, this imaginal potential resembles to your Dirac delta function. That's why I'm treating this kind of problem as a potential problem. I call it Dirac delta potential. Right? Okay. If you think about this Dirac delta, You know, it is, if I take the integral from minus infinity to infinity, you have the delta function, del of x, d of x. What is this equal to? Come on. This is equal to 1. Okay? It is that point. This is the only point that exists here. And everywhere there is freedom. There's only kinetic energy. You are not being exerted by any kind of force. And there is another important property of this Dirac delta. What's that? That is, if you have, say, because I have to use the eigenfunction, I would like to write down this as minus infinity to infinity psi of x delta of, because you can translate this delta, x minus a dx. And this is equal to what? Psi of x. In fact, psi of a. Right? This is another important property of Dirac delta function. So, I'm choosing the simplest of all potentials, because the other potentials are very, very crazy calculations. You have to do that, all algebra that's involved here. But let's go with this. Let's go with this problem. So what am I doing is I'm choosing my potential as Dirac delta potential. This is the potential that I'm choosing. All right? Okay. So if I choose this potential, it will be something like this. I'm choosing it in the negative direction because it gives me, it eases out some of the simple calculations. Because I always fail to keep the sign in most of the problems. But let's try. So what you have this point here, okay? And at this point, you feel a potential what? You feel a potential V0. So you have something left to this point. This point is x equal to 0. If you will go left to this point, you will have x less than 0. Right? If you go to the right, you will have x greater than 0. Okay? You have no potential, no potential, no potential. Then you have a point potential. And then again, there is no potential. There is no potential. So what am I trying to tell you is that the potential that you will feel is V0. But it is, what is the nature of this potential? Dirac delta potential. So this V0 is nothing, I'll choose it as minus alpha delta of x, where alpha is a constant, it's a number, right? Fine? So what you will have, what you expect now? You expect the three regions. You have the three regions. Now let me go back to our problems that we have already talked about. Infinite potential well. You can have infinite bound energy states. Then we talked about finite potential well. Now you will have finite number of bound states. And because yesterday you saw that number of bound states is proportional to the depth of the potential. More the depth, more is the number of bound states. It's dependent on the width of the potential. More the width, more will be the number of bound states. But now we are boiling down this to realize actually this problem to the Dirac delta nature. And I told you the nature of Dirac delta. It is just a point. So point, when you talk about the point, you fail to resolve it classically. So what we do here is we try to resolve this problem in vicinity of that point. And then we take a limit, tends to 0. This is how we can resolve the mathematical problems. So now what we have here? We have three regions. But see, the nature is such that I will call everything here as psi. Could you see the ideal nature of this problem? It's very idealistic. It's free. Then there is just one point. And then again there is freedom. Right? So I would like to write down the Schrödinger's equation now. So you will have a Schrödinger's equation in this region. It will have a solution. This region, it will have a solution. And then we will see how we will resolve this part, which is the potential whose geometry is, whose nature is like minus alpha delta x, where delta x is Dirac delta function. Is this clear? Okay, so what do we expect here? See, one thing is clear. Here you have only kinetic energy. Okay. Then you have Dirac delta potential. Then again you have kinetic energy. Now, if I write down the Schrödinger's equation, it will be d2 psi by dx2 plus, can I write something like this, minus 2m by h cross square, but I will choose this as minus e and psi equals 0. Right? Now see, this e in vicinity of, at the edge of this point, this e has to be what? It has to be less than that of, it has to be less, it has to be negative. Because I have chosen the potential in this direction, the e has to be negative. So in order to make this bracket, positive, I chose a negative here. But e is already what? Negative. So this thing is becoming numerically positive. Right? So now, what can I do here? I can write down d2 psi by dx2 minus k square psi equals 0. I think the same differential equation is applicable in the right hand side of this Dirac delta potential, because there is symmetry. There is symmetry. The universe and a point. Right? Okay. So now you have a second order differential equation, and how will you write its solution? Yeah? You write its solution as psi equals a e to the power of kx plus b e to the power of minus kx. Now you see, if it is from the left to right, you remember? Okay, what exists here? Imran, from left to right, what will exist out of the two? The negative will go here. Okay, when you move from left to the potential, this negative will go, we have already talked about it. So for that, to make this 0, because it doesn't have the physical implications, to make this 0, this b must be 0. So what will happen to your wave function? What will happen to psi? It will be just a e to the power of kx. Right? Okay, this is your left region. Now, what about the right hand side? What will be psi there? I got a, I got b. Now you have c e to the power of kx plus b e to the power of minus kx. Do you remember? When we talk about the right side, what goes? The positive. The positive goes. The positive doesn't make sense. So to make it 0, I will choose c equal to 0. So what you will have here? You will have psi equals b e to the power of minus kx. Is this clear? Okay, so now what is our problem looking like? Our problem is we have psi, and this psi is a e to the power of kx, and then you have what, d, is it d?
Yes.
Okay, d e to the power of minus kx. Right? Now see, now let me again go with my wave function, with my eigenfunction. So this is, okay, I'm not able to make a good diagram. because it's slipping out. So let me try it something like this. Okay, I'll choose a line here. I'll choose something broad here in terms of the wave function. Now this is my psi in the left. Okay, you can give some notation to it. Then you have another psi in the right. Okay, then you have that point of infinite density. You have that point of infinite potential. You have that point of infinite gravitational force. For psi to be useful, for psi to be acceptable, it must be continuous. It must be continuous at this point. That's the fundamental rule. It has to be continuous. So if it has to be continuous, you can say this a e to the power of kx is equal to d e to the power of minus kx. So this will lead you to a equal to d. Clear? So I can boil down this result to any of the two, a e to the power of minus k. I will take the mod of x here. You can choose it this way. Okay? Because it is the reflection. There's a pure symmetry. There's a beautiful symmetry in this problem. Whatever is in the right hand side, the same thing is in the left hand side, right? So I can write down this solution as a e to the power of minus k mod of x. Is this clear? Okay, so this is the another thing. Now, come on. Now see, I cannot do anything mathematically at this point. Can I do? No, I cannot do. I can reach to this point. So if I have to reach this point, I will have to use a limit. But to reach that point, I have to dissolve it. I have to dissolve it. I would like to take the 2 points. The point, say, this is minus e, and the point, say, plus e. Right? Okay. Now I want to write down the Schrodinger's equation. Where I want to write it? I want to write it at the point. This is just a point. It is not a pit. It is not a hole. It is just point. It is just mathematical point. So what you are going to do here? You would like to write down the Schrodinger's time independent equation. So what is that? That is d2 psi by dx2 plus 2m by h bar square e minus v naught of psi equals 0. Isn't it? This is the Schrodinger's time independent equation. But now I have to replace this v naught by minus alpha delta x. Because my potential is like drag delta, and I have defined that mathematically. So what will I write here? I will write d2 psi by dx2 plus 2m by h bar square e that will become plus alpha delta of x and psi of x. You know psi of x, okay? Psi of x is equal to 0. Right? Fine? Okay, nothing wrong with it. Now I would like to write down this. Okay, I can write down this as d2 psi by dx2 plus 2m by h bar square e psi. Okay, plus 2m by h bar square alpha delta of x psi of x. Okay, you understand this psi is that of x. It's a one-dimensional Dirac delta that we are talking about. Okay, now I have this differential equation. I want to integrate this, okay? I want to integrate this equation. So if I integrate it, what I'll have integral d2 psi by dx2 plus 2m by h bar square e integral psi of x d of x. Here you can have d of x also, okay, plus 2m by h bar square integral, alpha is out, then you will have psi of x, delta of x, d of x. Okay, what's the limit of?
Minus e.
It is from minus e to plus e. I'll use it there where I want it. Okay. Now you will immediately see that this point, this integral will lead to 0. This term will come out to be 0. You can use the boundary conditions and you can realize it fully. Now here, what you will be left with? One derivative will cancel with the integral. So you'll be left with one derivative. Okay? What you will be left with? You will be left with d psi by dx. I will keep a del here so that because there are limits, e minus e to plus e. Right? Then you have plus 2m alpha by h bar square, right? And then you have integral minus e to plus e. Then you have psi of x, delta of x, dx. And this thing is equal to 0. Right? Okay, fine? Okay. So here you can easily resolve this part. You can easily resolve this part because you remember that a e to the power of kx. Psi is equal to a e to the power of kx. You'll get d by dx, d psi by dx. Okay? Then you'll be using the values. What you will get? Can you tell me what you will get? It will be minus 2ak. Come on, you'll do it. Okay? This part will give you minus 2ak. Right? And this part will give us what? This part will give us psi of a. Right? So what you will be left with, and you will give the value to that psi. Do you remember the value? A e to the power of kx. So these exponentials will cancel. When these exponentials will cancel, you will get minus 2ak and then plus 2m alpha by h bar square. Here will be a. Are you getting it? Because the exponentials because you will say that the exponential is not equal to 0 and the rest that you have there is equal to 0. Are you getting it? Okay, this will be equal to what? This will be equal to 0. Right? Now I can easily see this a and a will cancel, isn't it? Okay, so what will be left with? This 2 and 2 will cancel. So what you will get? You will take this k on the other side. What you will get? Here, okay, minus. Okay, so what we are left with? So we are left with k equals m alpha by h bar square. But what was k chosen? It was under root of minus 2m e by h bar square. Wasn't it? It was like this. You remember? I chose the negative, then I incorporated the negative to make it consistent with e. Because e is negative, that will make it positive. So I can square it. You will have k square equal to minus 2m e by h bar square. So what do I need now? Okay, this is k square. So I would like to take square of this also. This will give me square, this will give me square, this will give me square, and this will become raised power 4. Right? So what you are left with? You are left with 2m. It is minus, okay? 2me by square equals m square alpha square by h bar raised power 4. Right? You can cancel this square with this 4, it will become square. You will cancel this m with square. So you will get E. And it has to be negative because if you see that the potential that I chose, it was in the negative direction. So what you are getting the energy. What do you get? Tell me, what do you get? What does it mean? What have you got? Come on, tell me. E is what? E is, yeah, what is it?
M.
Minus. It has to be minus m alpha square by 2. 2 is somewhere. 2 h bar square. What do you get from this equation? Tell me. Come on. No. How can you differentiate this thing from the problems that we have already talked about? Yes, it is bound. Beautiful. It is bound. We know that it's bound. But what's something that is very strange here? You see the power of this mathematical function, where you write down this function and you feel this function only at one point. Yeah, what's so great about this equation? You see, the greatness of this equation is that this energy is independent of the integral number. You will carry only one bound state. You will have only one, there is no n in it. Come on, look at this equation. Right? E equals n. You remember, in case of particle in infinite potential, well, it is n. It is dependent on n. Then the particle in finite potential, it is dependent on n. But here, you will have only one energy. Okay? And that energy is this. So this, I chose Dirac delta potential because I wanted you to give the feel of mathematics, that how mathematics works when we apply it to the real idealistic problems. So what do you conclude here? You conclude here that if you have a Dirac delta type potential, then whatever the energy will be, okay, it may be 4 here, 10 here, doesn't matter. You will have just one energy. That's why you remember when I said, imagine, I said you are free. You walk in this island, you walk in the universe. There's nothing. Nothing is hurting you. Nothing is exerting you. But you feel a point. You just feel a point. And when you leave that point, you feel as if nothing happened. Right? So here you have just one bound energy. You have just one bound state. Any questions? Come on, any questions? Come on. So I thank you all. Let's meet in our next